Okay, these are the day 5 notes, and we're continuing our discussion about exponential functions and situations that present themselves and can be modeled by those exponential functions. And one of those situations is watching a ball bounce on the ground. So if you've ever experienced this, you drop a ball from a certain height and it hits the ground, and it always bounces back, but it never bounces back to a point that's as high as it started from. And there's some physics going on there as to why it doesn't, but we see that this height then, gets shorter and shorter and shorter as that ball bounces until that ball finally doesn't really bounce anymore. And so that relationship is exponential. So it's kind of a cool phenomenon. So we're going to kind of use that as the frame of reference for this for these notes. We're dropping a racquetball from an initial height of 100 centimeters. So we have this initial height of 100 centimeters, our start value, so to speak, our start value. And it says their phone was used to record a video of the ball bouncing 6 times. And then they recorded the video. It says they recorded the height after each bounce, so they would analyze the video. You might do something similar to this in physics. They analyzed the video, recorded the height after each bounce, because it's hard to, know what the height is while it's moving. And then they watched that height decrease over this thing bouncing 6 times. So the data that they collected then is that we started, here's that start value again, of 100 centimeters, 100 centimeters, so a meter stick basically. And the first time it bounces and comes back up, it's only bouncing to a height of 58 centimeters. And then the next time it bounces and comes back up, it only bounces to a height of 27. And then the third time it bounces to a height of 12. And then it bounces to a height of 7. And then it bounces to a height of 4, and then it bounces to a height of 3, and then it's probably not bouncing high enough to really gauge its height after that. So they just stopped collecting data. So if you look at this, you can see that we have a start value, and that these values decrease over time, so we have some sort of decay problem. And so we should expect then that we have some sort of multiplier that is between 0 and 1, just like we've been discussing for the last couple of sections. So we are going to model this as a y equals a b to the x, right, where a is our start value, and b is our rate or our multiplier, however you want to call that. This is our rate, our constant multiplier. And so that, that we find that rate by multiplying, or in this case, dividing the next term by the previous term, right? So in other words, to find that constant, if this table were a table that was horizontal, like we had earlier in the section, we would say, okay, well, 100 times something equals 58, right? And the way we can find that times something, okay, is to take a ratio of 58 and divide it by 100. So that 100 times 58 divided by 100, which means that multiplier is 0.58. And then we're going to look at this multiplier, and it should be the same. However, if we take this 27 divided by 58, that's the next multiplier, we notice that it's not different. And the reason why, or it's not the same, excuse me. And the reason why it's not the same is because this is data that comes from an experiment, and the experiment isn't going to be a perfect exponential. So we're going to have to do some averaging of this data. And so if we keep coming up with this multiplier, this next multiplier. Notice I'm just making a fraction. It's 12 over 27, right? The new one over the old one, and that equals 0.44. And then we look at the next one, so this would be times 7 over 12, and 7 over 12 is 0.58. And then this next one is times 4 over 7, and 4 divided by 7 is 0.57. And then this last one is times 3 over 4, and 3 over 4 is 0.75. And actually, maybe we should put those, because that first one doesn't really have a ratio, so to speak. So we should put those there. And let's update then our arrows. So it would be there's our ratio for the ratio of the current height to the previous height. And so if you notice, these are not the same. Ideally, theoretically, they should be. So so it says, does the data seem to follow a linear or exponential pattern? And we know this is exponential. We know that we have a percentage of the previous value. If we graph it, you know, if we could graph this, we start at 100. We start at 100. Our first bounce is at 58, which is probably about right there. Our second bounce is at 27, which is about right there. Our third bounce is at 7, which is roughly there. Then we go to maybe 4 and 3. So definitely not linear. We definitely have something that is curved. And so this definitely is our decay curve. So the graph is curved. And the common ratio is similar, but it's not super consistent. It has a common ratio, and they're similar values because of the experimental nature here. They're close, and that's all that really matters right now. So we want to be able to model this. So we're going to model this with an exponential. And so we know the y-intercept is 100. That's our start value. And then, and the meaning, again, we covered that a couple of times. That's our start value. That's our A, so to speak, in the general form of A times the common ratio B to the x power. And so this is where we kind of have to say, well, we know this is curved, and so we need a consistent ratio. So we're going to average what we have. So what did we start out with here? We started out with 0.58, then 0.47. So we're going to average that. 0.58 plus 0.47 plus 0.44 plus 0.58 plus 0.57 plus 0.75, all over, got 1, 2, 3, 4, 5, 6 common ratios. And so that average then, and that's going to be our B then. That's our common ratio. That average then is about 0.565. So that common ratio, in the context of this experiment, it kind of speaks to the elasticity of the ball, right? If it was a super ball, we would get as much a common ratio that would be much closer to 1 because that super ball would bounce pretty close back to its original height. If we had a really flat beach ball, it might only bounce a couple of times, or a really flat soccer ball or something like that. So the height function then, we'll call it h of x, then is going to be a times b to the x power. So our a is 100, and our b is 0.565, and that's going to be to the x power. And you notice that that common ratio, or that b value, is between 0 and 1, and that gets us our dk, right? It doesn't pop back up to the same height. And so we can use that to predict the height after 10 bounces. So we want to know what happens when it bounces 10 times. So 100 times 0.565 to the 10, it's going to have a height of 0.332 centimeters. So it's not even going to bounce a centimeter off the ground. Centimeters, roughly maybe a ½ inch, just to give you a frame of reference. Okay, so the idea then is to use this as a model, right? We've got this contextual situation of a ball bouncing, and it can be modeled with an exponential function. And so what we want to walk away with in terms of skills that, the mathematical skills we need to solve problems like this, is we need to be able to write an exponential model. So that's the first thing. And so we are looking at one, to identify A, that's the start value. And 2, we need to identify, or in this case calculate, B, that's the ratio. And then we're going to be able to write that as A times B to the x power. And then we want, we have a second learning target. We didn't really talk about this too much in the notes, but I'm going to kind of preview it and checking your understanding. We want to be able to write an equation. We kind of did it, right? An equation from 2 points. And we kind of did it with the table, right? We had 2 different heights, and we found the common ratio, and we were able to write the equation that way. And so, so we did that when we just had to average it to find a good common ratio that would be applicable throughout the whole bouncing action. And so we'll kind of preview that down below in just a second. I just want to get the third learning target here. And really, I think these two are really closely related. This is from a table. We need to be able to find, or a graph, I guess, the y-intercept, or the start value. We need to be able to find the common ratio, or calculate the common ratio. We need to be able to do those sort of things. And then, write our equation based on that. So I don't know, I see a lot of repetition in learning target 1, 2, and 3. Let's talk a little bit more about that learning target 2 in the context of this example down here. So we have Halloween, we have a face group book for the Octopus Fan Club, Octonation. It's got 230 members. So we start out with 230 members. 2 days later, there are 295 members. Assuming that the growth is exponential, complete the table. So from those 2 points, we're going to write an equation, right? And like I said, we did this a little bit with the ball bouncing when it started at 100, and then after the first bounce, it was at 58 centimeters. We use those 2 points to come up with a common ratio. So that's what we're doing here. So we need that common ratio. And I called it B, you could call it R too for common ratio. And so that B is the new point, 295, divided by the old point, 230. And so that common ratio is 295 divided by 230 is 1.13. And we're going to use that common ratio. So now we're going to be able to do this to come up with the rest of the table, and we'll be able to write the equation in A times B to the X form. So like I said, I see a lot of duplication in those learning targets up above. So I'm going to let you finish that as you check your understanding, and then you can check your solution to that against the notes, either in Blackboard or in the front of the room. And then I've got some ideas here to give you guidance on the remaining. Check your understanding questions, and then the homework is more of those tabular and graphical type problems to come up